Welcome to the Design and Control of Concrete Mixtures. We will be covering Chapter 7, Chemical Admixtures for Concrete. In this presentation, we will cover a variety of chemical admixtures, including air entraining, water reducing, set controlling, and other admixtures. We will end the discussion with admixture compatibility and an overview of storing and dispensing of chemical admixtures. Chemical admixtures are those ingredients in concrete other than hydraulic cement, supplementary cementitious materials, water, aggregates, and fiber reinforcement that are added to the mixture immediately before or during mixing. There are a variety of chemical admixtures available for use in concrete mixtures to modify fresh and hardened concrete properties. The major reasons for using chemical admixtures in concrete mixtures are to achieve certain properties in concrete more effectively than by other means, to maintain the quality of concrete during the stages of mixing, transporting, placing, finishing, and curing, to overcome certain emergencies during concrete operations, and economy. Despite these considerations, no admixture of any type or amount is a substitute for good concreting practice. Chemical admixtures considered for use in concrete should meet applicable specifications as presented in this table and on the next slide. Chemical admixtures can be classified by function as follows: air entraining, normal, mid-range, and high-range water reducing, set accelerating, set retarding, hydration control, rheology modifying, corrosion inhibitors, shrinkage reducers, permeability reducing admixtures, alkali silica reactivity inhibitors, coloring admixtures, and miscellaneous admixtures such as workability, bonding, grouting, gas forming, anti-washout, foaming, and pumping admixtures. Trial mixtures should be made with the admixture and the other concrete ingredients at the temperature and relative humidity anticipated during placement. Then observations can be made on the compatibility of the admixture with other ingredients, as well as its effects on the properties of the fresh and hardened concrete. The amount of admixture recommended by the manufacturer should be used, or the optimum dosage should be verified by laboratory testing. One of the greatest advances in concrete technology was the development of air-entrained concrete in the mid-1930s. Air entrainment dramatically improves the durability of concrete exposed to cycles of freezing and thawing and de-icer chemicals. Air-entraining concrete is produced by using either an air-entraining cement by adding an air-entraining admixture during batching, or a combination of these approaches. The primary ingredients used in air-entraining admixtures are listed here, including chemical descriptions and performance characteristics. Numerous commercial air-entraining admixtures manufactured from a variety of materials are available. Air-entraining admixtures are surfactants that concentrate at the air-water interface and reduce the surface tension, encouraging the formation of microscopic bubbles during the mixing process. Air-entraining admixtures typically have a negatively charged head, which is hydrophilic and attracts water, and a hydrophobic tail, which repels water. The hydrophobic end is attracted to the air within bubbles generated during the mixing process. The polar end, which is hydrophilic, orients itself toward water. The air-entraining admixture forms a tough, water-repelling film similar to a soap film, with sufficient strength and elasticity to contain and stabilize the air bubbles. The hydrophobic film also keeps water out of the bubbles. The stirring and kneading action of mechanical mixing disperses the air bubbles. The charge around each bubble leads to repulsive forces that prevent the coalescence of bubbles. The surface charge causes the air bubble to be adhered to the charged surfaces of cement and aggregate particles. The fine aggregate particles also act as a three-dimensional grid to help hold the bubbles in the mixture. This improves the cohesion of the mixture and further stabilizes the air bubbles. Entrained air bubbles are not like entrapped air voids, which occur in all concretes as a result of mixing, handling, and placing. Intentionally, entrained air bubbles are extremely small in size, between 10 to 100 in diameter, while entrapped voids are usually 1,000 or 1 millimeter or larger. As shown here, the bubbles are not interconnected. They are well dispersed and randomly distributed. The amount of air entrained in concrete for a given dose of admixture depends on materials, mixture proportions, methods of transport, placing and finishing methods, and curing. Variations in air content can be expected with variations in aggregate proportions and gradation, mixing time and intensity, temperature, and slump. The order of batching and mixing concrete ingredients when using an air entraining admixture can also have a significant influence on the amount of air entrained. When entrained air is excessive, it can be reduced by using one of the following defoaming agents: tributyl phosphate, dibutyl phthalate, octyl alcohol, water-insoluble esters of carbonic acid and boric acid, and silicones. The presence of a finely distributed network of bubbles has a significant impact on the properties of plastic concrete. Entrained air improves the workability of concrete. Because of improved workability with entrained air, water and sand content can be reduced significantly, as shown in these graphs. A volume of air-entrained concrete requires less water than an equal volume of non-air entrained concrete of the same consistency and maximum size aggregate. Freshly mixed concrete containing entrained air is cohesive, looks and feels fatty or workable, and can usually be handled with ease. On the other hand, high air contents can make a mixture sticky and more difficult to finish. Furthermore, the air bubbles reduce the tendency for segregation and bleeding. Improvements in the performance of hardened concrete obviously include improved resistance to freezing and thawing, and de-icer salt scalding. Furthermore, the incorporation of air also results in a reduced permeability and possible improved resistance to sulfate attack and alkali silica reactivity. The single detrimental effect is that an increase in air content results in a decrease in the strength of the concrete. When the air content is maintained constant, strength varies inversely with the water-cement ratio. A good rule of thumb is that each 1% increase in air content is accompanied by 5% to 6% reduction in strength.